go live. Good morning, everyone. Sorry for the slight delay. There we are with all our energy for today. I wanted to see that, given that people have seen Huffman coding, some of you might have also seen the relation to entropy. And I'd like to get your thoughts on this. I'll leave it open and first cover a couple of announcements. It's virtually the same as yesterday, so not a lot of new things. I wanted to make a remark about the class tests. It has happened for a few students that first of all, I released the results from class tests 2 and 3 that you already submitted on Friday. I should have done that earlier, but I frankly forgot that I have to explicitly release it. So now you can check what happened and what your answer was and what the correct answer was. You might not see the correct answer yet. I have to also explicitly allow that. I'll do that later then. But in any case, some noticed that they gave a wrong answer or was marked wrong because the format was incorrect. So please use the practice version of the class tests in the future so you don't lose easy earned marks just because you have the incorrect format for the answer. I want these to be auto-marked so that we can have many of these and they're cheap to do and a good practice opportunity for you. And that's why I always do an identical copy in the practice version, so please make use of that. Some video groups, as I announced yesterday, didn't submit this supplementary description, who did what, etc. Please do that in case I marked your submission for resubmit. And we have a couple of upcoming deadlines. The bamboo puzzle on Friday, as you probably are aware, and the next class tests the Friday next week and the Friday that week after, class tests 4 and 5. Yeah, as always, my call for Campus Wire, but you're probably well aware of this one. Let's see how the results look like here. So it seems a few people, a third, have seen the relation, so maybe I don't have to go through all the details, but then some also haven't, and some have never heard what entropy is, which is also fine. This just shows again that the background is very different. Okay, let's stop this for now, and we'll go back to where we left off. We're in the middle of discussing Huffman's algorithm, so maybe just briefly go back and give the proper context. We're talking about Huffman codes which can exploit situations like this, where you have to encode an alphabet where the characters have different frequencies. Some are very frequent and others hardly ever occur. So you want to find codes that make the more frequent ones cheap, giving them a short code, and give a longer code to the other ones. As always, if you have questions, please use the Q&A or the Campus Wire back channel. I keep repeating that just to remind you. So how did Huffman's algorithm achieve this? It is actually possible to find an optimal code for this scenario, the one that minimizes this expected code length, where you have the sum of all the characters, you multiply their weight with the length of the code word they get assigned, the number of bits they get assigned. And this is the quantity we want to minimize, and we could achieve this by, you remember this, always finding two characters that have minimal current weight and then group them together. And we maintain these trees in a priority queue where we sum up the weights of all the characters in this subtree. So that was a very simple algorithm. And we argued yesterday that it actually finds the best possible code in all instances, no matter what the weights are like. What we didn't talk about yesterday is how good that actually is. Okay, caffeinated now for the rest of the session. So let's continue here. We talked about Huffman coding and that it always constructs a prefix-free code for a given alphabet with given weights, so that it minimizes this sum, the expected code word length. But how good that is remains to be seen. And luckily, in the case of Huffman codes, and in this case of prefix-free codes, we have a fairly complete understanding of what happens. And this is where entropy comes in. That's why I asked before how many people have seen this. So maybe let me just show the answers here one more time, also in the main video. So I asked you if you know what entropy in this information theoretic sense is and how it relates to Huffman coding. And quite a few people do know, but some others have never heard it. So I'll try to give somewhat a brief introduction without spending a heck of a lot of time. So what is entropy? Simply speaking, it's this definition that you see on the slide. It's defined for a set of probabilities. So we assume we have a random outcome here, numbers 1 up to n, but it could be other objects. The important thing is that we have a finite number of these, or a discrete number of outcomes, and the probabilities are given like this. So as always, the probabilities are between 0 and 1, and they sum to 1. That goes without saying whenever we say probabilities. And then the entropy is defined as this sum. We take the sum of all possible outcomes, the probability for that, and then log of 1 over the probability. Another way to write this is saying that it is an expected value over log of 1 over the probability for the outcome. That's just another way of writing this sum, because it's a sum that weighs things with the probability. That is an expectation by definition, but we will not really dwell on this interpretation much. That's just a definition. So maybe before we continue with this, we might want a small, tiny example. So say you have a fair die with a usual one, not the Dungeons and Dragons version with whatever many faces, with just 6 faces, the usual one. And fair means so all of the outcomes 1 to 6 happens with probability 1 over 6. So what is the entropy of this distribution, of this random variable of the faces of a die? Well, just look at the definition. So if I write it like this, I would have to copy 1 over 6 times, but I'm relying on your intuition, on your ability to guess that from the context. What it is the sum over, well, 6 times the same thing. So we can write it like that, but it's really a constant term inside the sum. And then we have 1 over 6, all right, just do it in slow-mo. It's 6 times the same thing and weight by 1 over 6. So that is a 1 times, and then log of 1 over, that's log of 6, right? And well, whatever that is, can we get log of, okay, this, maybe I should have prepared it. It's some number between 0 and 3, between 2 and 3. And well, whatever it is, maybe someone wants to compute it and send it in the chat or so, but it doesn't really matter much. So entropy has this feature that it sometimes has fractional values. Not always, though. Let's do another small example, a fair coin. So we have heads and tails, each with probability 1/2. If we do the same calculation, everything remains the same except that this is a 1/1/2. So it's log of 2, and my log is always base 2, right? So that's just 1. So here the entropy is exactly 1. Okay, those are two simple examples. In the general case, if the probabilities are not all the same, then the sum doesn't simplify as easily, but you can still compute this for any given set of probabilities. What we need entropy for is as a measure of information content of a distribution. So how is that to be understood? In a sense, people often say it's the surprise, the amount of surprise that you get when you learn the outcome of such a random experiment. So say you throw a random die and you learn it came up with 5. How surprised are you to find 5? Well, entropy says you should be surprised 2 point something bits, whatever log of 2 is, log of 6 is. Okay, that's not very intuitive. More intuitive is using something like this 20 questions game. And I want to introduce this here in a very specific setting, namely the one that we will need for Huffman coding later on. So the game is as follows. You start with the unit intervals 0 to 1. Then I think about an interval, this little red one. It's somewhere in this unit interval. It's a subset of the unit interval, some interval somewhere. And then you start guessing. And your first question, before you start, you know nothing except that it's somewhere in the unit interval. And now you can guess, you can ask questions. Is your interval contained left of a certain point or right of a certain point? And a moment's reflection shows that the best you can do is to always ask, is it left or right of the middle point? Okay. And we'll make our life simple here by assuming that you never hit the interval. You would have to define this a little different. It works cleanest if the intervals have specific numbers only as their endpoints. So let's just see how this game goes in the cleanest version. Before you ask the first question, you know nothing. It could be anywhere. Then you ask, is it left or right of the point 1/2? And in this case, I answer, it's above 1/2. And so you have learned something, and you have spent one question. You have narrowed down the interval to this, this range 1/2 up to 1. Then you continue doing this. You ask, is it above or below 3/4? And I say, well, it's below. So you have learned a bit more, and you've spent 2 questions, and that's 2 bits of information. 2 yes/no questions. And you keep going. You ask one more question. I again say it's in the upper half. Okay, you learned that. And one more time, and then I say, well, yep, I'm spanning the range that you have. I extend over the entire thing. And so with 4 questions, you have learned what my interval is. In this clean way, that's what it works out like. And the observation to make here is that if you look at the length of this interval and you take log of 1 over the length, that's log of 1 over the probability for a random point on the unit interval to randomly fall inside my interval, then you get exactly 4. So if you want to think about this game, again, maybe a cleaner way is to think about not this interval as an interval, but you throw a random point somewhere. And you're asking, is it inside this red interval or no? And you know which intervals are possible up front. This we'll come back to this in the context of Huffman coding. Okay, so intuitively, what happens is we need to cut our interval in half that many times before we can reach the conclusion, potentially, if we're lucky in how the numbers work out. We need at least that many halving steps before we can reach something that's small enough to be covered by this interval that you're looking for. And that's the way to think about entropy. It's a lower bound. It's what you definitely have to spend. It's not necessarily always attainable. So another way of saying the same thing is the entropy expresses the expected number of bits of yes/no questions you have to ask that are needed to nail down a random value when what you know about the random value is some discrete outcome, like it lies in the red interval. I hope this gives you some intuition for why this term makes sense. In simple terms, it is how often you have to cut things in half before you reach the size of this interval. What is the connection with Huffman codes? This entropy was just a definition that came out of nowhere. There's a theory behind this. It's called Shannon entropy because Claude Shannon introduced this, over 70 years ago. And it was very successful in many different fields. But the connection to Huffman codes is actually very intimate and also long known. The entropy formula essentially is a guidance to design good codes, because if you look at this again, this formula is essentially looking like our formula for the expected code word length for the quality of a prefix-free code, except that here we had this term stating the length of the code word we assign to an outcome, and now it's this term, and we say this is what we definitely need. So if we could encode the outcome I with log of 1 over p of I, p for I bits, we would be very happy. That's essentially the ideal code word length. Unfortunately, we cannot really do this in many cases. Say this log of 1 over pi works out to be 1.5. How should we assign 1.5 bits? This sounds, it's definitely not possible to assign a code word of length 1.5 bits. Not if you use binary encoding, but it is not as weird as it may sound at first. You can actually do something like this, where you achieve this on average, or you achieve this using different elementary units than bits. But we will not cover this here. And definitely in a Huffman code, the code words you assign have to be binary strings, and they can have 1 bit or 2 bits, but not 1.5. So this is not generally possible to achieve the entropy with Huffman codes, but we can at least show something very close to that. And the statement here is, if we have an optimal code, a Huffman code, and its expected code word length, then it is never better than the entropy. This is what I tried to convince you of from before. The entropy is, in a sense, a much more general lower bound. You cannot possibly get by with fewer bits, just because you have to learn the information. You have to cut down this interval often enough. But more importantly, Huffman codes are also never much worse. If you add 1 to the entropy, that's an upper bound for the quality of the code that you get from Huffman's algorithm. And what is the entropy in this case? Just to be clear, because we allow the weights in Huffman coding are arbitrary. They don't necessarily sum to 1, so you just have to renormalize those, divide by the total of all the weights, and then you get a probability distribution. So there's nothing magic in this formula for H. It's just normalizing the weights. Let's see how we can prove this. And the proof has 2 parts, because we have to prove 2 statements. We have this inequality and this inequality. And we will look at the first one first, because it's a little simpler. because people have seen this. Maybe I don't spend too much time on this proof, or some people have seen this. It relies on two other results that are simple results from mathematics, but I don't want to prove them in detail here. But I think the main message here is that entropy and Huffman codes might seem not so much related at first, but there is an intimate relationship, and that's what is in this definition. We start building a Huffman code with certain probabilities. So I will essentially call this P1 and up to P sigma. Just the normalized weights give us probabilities. We'd like to build a code, we build a code in Huffman's algorithm based on these probabilities. Once we have that code, or any code really, we can assign different probabilities based on the outcome, based on the code word lengths. And these are essentially given like this. So if you take negative powers of 2, so say if your code is like this, let's do a tiny example, A, B, C. Maybe A is just a 1, B is 0, 0, and C is 0, 1. Then you would assign A a probability of 1/2. Maybe let's add that into the table instead. Well, let's write it QC. So you would assign 1/2, 1/4, and 1/4 to these each. So you might not have had these probabilities when you started, but probably something in a sense close to it, approximate to it. Otherwise, Huffman wouldn't have built this code. But you could do this for any prefix-free code. It doesn't have to be a Huffman code. Now, there's first inequality, Kraft's inequality. It basically just says that if you sum up these QI, it's at most 1. And in the way Huffman codes are built, it's actually equal to 1. And that one just says if you draw the code trie for this code, let's do that in our tiny example. So we have B, C, and A. What Kraft's inequality says is, suppose each node splits probability in 1/2 to each side. Then I can always project this onto the unit interval. And then every node splits this interval in half. And a leaf covers all the range that is at this point. So this one covers the entire, let's make this a little nicer, covers the entire range. So A has 1/2 weight in this code. Similarly, if you go one further down, then this node splits that here at a quarter. And then B and C each span this range. And so they get 1/4 each. Okay, that's a general mapping how we can assign. That's essentially what the QI does. And now Kraft's inequality says that if I add these up, they're at most 1. And that's obvious because I started with the unit interval. And whenever I went down to an internal node, I just cut things in half. How could I ever have overlaps so that the sums get bigger than 1? That can never happen if I just split things here with 1/2, 1/2 each. Okay, so that's Kraft's inequality. And if we have any set of numbers between 0 and 1 that sum to at most 1, we can use this second inequality, which is called Gibbs inequality. And that is basically this, which is true for any QI in 0, 1, so that they sum up to at most 1. That's another inequality that you can prove analytically using properties of the logarithm. So I don't want to do that here. my message here is, if you've shown Kraft's inequality, you can use Gibbs inequality, so you can use this middle statement, which means you start with the entropy, but now you replace pi in the log by this other probability qi, or this other number, and you get only bigger by doing that. Intuitively, it says if you've built a code for pi with the best possible code word lengths, and you substitute the code built for some different probabilities, qi, you only get worse. That's what Gibbs inequality intuitively says. And that's, of course, also how we can interpret it for Huffman codes. Because this here is just the entropy, whereas this here is the code word length for our Huffman code, or for our code E, no matter what code it is. So the code word length for any prefix-free code is at least as long as h. That's the statement that we can prove here, and it's indeed true for any prefix-free code E, this lower bound. It doesn't have to be a Huffman code. The second part of the proof is this upper bound. So we now want to show that we can always have at most h plus 1 as the code word length in a Huffman code. This statement needs a Huffman code. And I'm aware that this looks a little scary, but the argument is not that tough. I just wanted to spell it out on the slides. But let's go through this a bit briefly. We start with the same trick. We define QIs that will correspond to code word lengths, but we don't have a code yet that is convenient for this. Instead, we do something slightly different. We take the ideal code word length, so our log 1 over pi, that was the ideal code word length from entropy. Now, we know we cannot usually achieve this because it might be a fractional number. So we round up. We cannot round down, that would be the entropy bound, but we can round up and try if we can achieve that. And the thing is, yes, the answer is yes, we can do this. So we take the ideal code word length, round it up, and then define a set of QIs as if we had this code already. So 2 to the minus of this rounded up code word length. So all the QI are powers of 2, negative powers of 2. Can be 1/2, 1/4, 1/8, 1/16, and so forth. Now, before we continue, let's observe that if I sum up this sum, pi here, but qi there, by definition, that is just this. If you just insert that and notice that the 1 over and the log just cancel the minus and the power 2 to the power, then this is the same as this. And now, because this term is always at most 1 bigger than the not rounded one, you can pull the 1 out of the sum, and then you're left with the entropy. Okay, so that's the first step. If we can achieve a code that has qi as the induced probabilities, we're good. Or if we have the rounded up ideal code word lengths, we're good. And now we will construct such a code word length. So again, this here is nothing but log of 1 over pi rounded up. It's just a fancy way of writing it, but it's convenient to use it that way. So we construct a code E prime so that all the code words are at most that long. And just by renaming the alphabet, we can assume that the alphabet is sorted so that the first character is the least frequent one. Now we construct this code very similar to how Huffman works, but with a very slight twist. If we just have 2 symbols in our alphabet, then there's not much we can do. We can assign the 0 bit to 1 and the 1 bit to with the other outcome. And we observe that then here, the 2 probabilities have to be at most 1 each, at most 1/2 each. Or the the qi don't have to sum to 1, so I shouldn't call them probabilities, but the weights qi are at most 1/2 because you start with something, the pi are less than 1, so that means this 1 over pi is bigger than 1, so log is at least 1, and if you round up, that's at least 2, and then, 2 to the minus 2 is already 1. 2 to the minus 1 is already 1/2, so there you go. So that part's fine. The code word with 1 bit is not too long. If we have more than 2 letters, then we do the same step as in Huffman. We take the 2 with the least frequency, merge them into a super character. But now, the key step that's different from Huffman's algorithm is this. We don't assign the sum of the weights. We assign twice the bigger weight. And then we recurse and compute based on the new weights, the rest of the tree. Okay, so the rest of the construction is the same. But why is this allowed here? Why can we do this? If the 2 weights are actually the same, then this is just a fancy way of saying we sum up. But otherwise, if the 2 are different, that means that Q1 is the unique smallest value in this collection because things are sorted. And it also means because of these powers of 2, you can actually replace Q1 by Q2. Let's do an example. Say we have 1/16, then 1/8. Maybe I'll just draw it on the line instead. So here's a half, a quarter, an eighth, a 16th. So here's a 16th. Now, suppose we have a couple of 8s, like maybe 4 things. And another 1/4. Okay. And you notice I already left gaps here because the thing is, if this is our 1/16 and it's the only one, the next bigger is a 1/8. So we necessarily have a gap of 1/16 because all the other bigger numbers are multiples of 1/8 because they're negative powers of 2. So there's no way anyone can take up this slack of 1/16. But we know that these numbers sum to at most 1. That's from Kraft's inequality again. And because the p sum to at most 1. So because the q, it's maybe something to note here. The qi sum to at most 1. So there's no way how anyone could eat up this slack. So we might as well treat the 1/16 as another 1/8. And nothing else really changes. Now we only make a stronger requirement for this character. We want to have it higher in the tree. But it turns out this is fine. It just works out recursively. If you look at what you get from the inductive hypothesis for the super character, then it's the same statement with a new weight, and that's twice the big weight. That works out as this minus 1. And so because Q1 is at most Q2, that's good enough to bound the code word length for both of these characters. So we've constructed this way a code that has the ideal code word length rounded up. It's not the exact ideal code word length that the entropy has, but it's the closest you can imagine to get to it if you take every individual code word and just round it up. As this proof shows, this sometimes even leaves a little bit of slack. By rounding every code word up, you actually are stricter than necessary. It is potentially possible to round some of them down, but only some of them. It won't work if you round everything down, and you can't really rely on it. If in the worst case, you will have to round everything up. well, maybe not. In the worst case, not sure if you can if you can find an example where you can never round down. That seems counterintuitive. But the construction works if you round everything up, and it gives you the bound of h plus 1, and you can construct examples that come very close to this. Now the final step that's missing is, because Huffman constructs an optimal code for given weights, it is for the weights pi, it can't be worse than the code we just constructed. It's one other code for the same characters, so we might as well use it, but our Huffman code is never worse than this code. And the lengths of that code, we've just bounded that each of these code words is at most that long. So I just inserted that into the definition of L. And that again is at most h plus 1, as we've just shown at the beginning of this proof. So in total, we've proven this second statement as well. And in a constructive way, if you want, we can construct something that is like a Huffman code. It just is a slight twist in that we add this slack in the weight to make the construction cleaner. It's not obvious if you actually have to do this, and Huffman codes will never be worse, so you might not care. You can always construct your Huffman code with the same algorithm, and you can immediately get the guarantee that its expected code word length is at most h plus 1. Let's see if you're still with me, and I'll ask this little nitty question that asks to relate Huffman codes with some fixed length coding. I'm not saying what this fixed length encoding looks like. You're just supposed to compare this in the most general setting you can think of. So please have a go at this. When is Huffman coding more efficient than a fixed length encoding? And by more efficient, I think more precisely I would say more or at least as efficient as a fixed length coding. I'll give you a minute to digest this. And as always, we've had some 23 or so in the first question. So I'd love to see at least 20, better 25 people in the question. Well, YouTube claims I only have 20 viewers right now, so maybe 20 is already the limit for today. But we can do a few more. 13 is not quite 20. 14. Shall we leave it at, 17. Okay, 18. Thanks, guys. Good. Okay, maybe let's lock it in now then. And here's the results. So people have voted for very different things. I decided to mark these two correct in the strictest way of interpreting it. First of all, if you define more efficient, as I said, as never worse, then Huffman coding is, oops, I wanted to lock this really. Huffman coding is never worse than any other code, in particular a fixed length code. So it's always fine to use Huffman instead. You can never really pay more in the sense of code word length. The other statement here is also true. If you want to have a guarantee that you're strictly improving over a fixed length encoding, these statements here are not really enough. You need this, because remember what we've just shown, L of E is at most h plus 1, and it can be arbitrarily close to that. even though we don't know how h relates in general to log of sigma, the uniform distribution that would be optimal for the fixed length code, if this is less than log sigma minus 1, then that eats up the plus 1. So you would have log sigma, and that is the length of your fixed code. And here we have a strictly less sign. So in this, if you can show this, then your Huffman code is definitely better than a fixed length code. Okay, thanks for participating with this. That brings me to the end of the Huffman code section. I just want to recap how the actual encoding algorithm works. So there's two phases, of course. There's two algorithms, of course, one for encoding and one for decoding. Encoding is slightly more complicated. There's two passes. The first one is we count all the characters in the text, in the source text, and count how often they occur. We need these frequency counts as weights for our Huffman code. In the previous construction, I always said, well, the weights are given, they're part of the input. But for encoding, you really rely on them to come from the text. So you start reading the text and you keep counting all the characters, and that's the weights you use for the Huffman codes. That construction is as you've seen in detail above. Now for encoding the source text, we actually have to store the Huffman code in one way or another. There's smarter and less smart ways to do it. I'll skip that part for this module. You can check the textbook from Sedgwick and Wayne. They discuss one option, a simple one. There's other options that are a little more space efficient potentially. So you have to store the code itself, and then in the second pass only, you use the code to encode all the characters in the source text. Okay. Now you will practice this in the tutorials in more detail. At least this second pass. We'll omit the encoding of the code, but the rest you will do. To decode, you first decode the code from, well, using a fixed encoding of the code. You have to decide on this, but again, we'll skip this. So we assume we already have the code read. And then you decode bit by bit from the coded text. Using the code trie, you just walk down the trie, and whenever you reach a leaf, you can output the next character, and that's it. As you notice, decoding is much simpler and also faster to execute. And that's not atypical in compression. You will see this happening again and again. So what have we seen about Huffman coding? The running time to construct the code is essentially sigma log sigma. That comes from the time to sort the characters by weights. Now, if the weights are smaller numbers, we can potentially sort faster than this. But if the text is very big, then the frequency counts will be way bigger than the alphabet size. So it's questionable what the complexity is then. You have to look at the parameters. But sigma log sigma is always possible with a comparison-based sorting method. Well, you can either sort up front or you build the priority queue, which is another way of sorting. So you get the sigma log sigma from the delete min steps and the inserts. Yeah, as an aside, there's a different algorithm that doesn't rely on a priority queue. If you have the characters already sorted by weight, you can do it in linear time. But we'll not discuss the details about this. The encoding itself is very fast. N is for the number of characters in the text, and C is the length of the code. So you have to, N is the number of characters in the source text. I should be explicit. So you read every character in the source text, obviously, but you also have to write the output. So this is the best you can hope for. There's no way to beat this apart from constant factors. Huffman codes in isolation might not be very widespread because, well, they tend to have some overhead coming from the fact that they have to fix an alphabet and have to fix weights, etc. But it is a vital component in all sorts of more advanced coding methods. So there's many variations that are in use, and you will find it as a building block in many more complicated encoding methods. We'll discuss that a bit later in this unit. So again, the good thing is it is a very clean, theoretically well understood method. It gives you the optimal prefix-free code, the optimal prefix-free character encoding. So it's the best possible you can do if you insist on encoding every character by itself. It's very fast for decoding. A slight downside is this two-pass approach for encoding. It means that you cannot use it in a streaming mode where you have just data flowing by and you have to process it as it comes. The two passes seem to work against this. There's hacks in practice to avoid this. You can restart after a certain block, or you can use adaptive variants. So there's a variant of Huffman coding that always maintains the best code for the prefix seen so far, but we'll not discuss these advanced topics. And another downside that's hard to overcome is you have to store the code alongside with the coded text, and that might lead to expansion. It might make the text bigger than what you started with if you're unlucky. But remember, we'll have to live with this fact there's no free lunch in compression, and in many cases, Huffman does achieve significant compression. I think that's a brilliant point to take a short break. So let's say we continue in 5 minutes. And let me add the page here. So let's do 54. And that's a great time for you to think of questions and put them in the chat. Here's the watch. See you in 5 minutes. All right, almost time over. Ready to collect your thoughts again. Hope you're ready for the next part. Let's get this out of the way. And there we go. In the first part of the compression chapter, we talked about how to exploit character frequencies. In this next part, we will talk about repetitive parts in the text and how to exploit this. And we will see the Lempel-Ziff methods as one core representative of this family of compression methods. So it turns out that many natural texts have a certain type of redundancy that is not well reflected by character frequencies. Here I listed some example of a text that might not be the very most natural one, but it's definitely a very repetitive one. But if you were to count how often the characters occur in this text, you will find that it's not that unbalanced. In a sense, if you make this very, very long, then all the characters will occur roughly as many times as if you were just looking at the first copy of this sentence. And that's a standard English sentence with no bigger redundancy than usual. So we would essentially pay the cost of the number of copies times the cost for storing one copy. Well, in fact, the text is just the very same sentence over and over again, pages over pages. So that doesn't seem to capture the redundancy in this case. Character frequencies are just not seeing this type of long distance redundancy. And we'll see this often in natural language text, but also in other types of data. DNA sequences tend to have the same type of long range copies or almost identical copies. And character frequencies don't capture this. In a sense here, what we would like to do is go away from character encodings. As long as we're encoding every character in isolation using the same code, there's no chance we will capture this sort of redundancy, of repetition. As a first method, a first simple method that falls into this category, we'll look at run length encoding. For two reasons. One, because it's the easiest method that does exploit repetitiveness in a certain way, even though only in the simplest form. But also it is another building block that for modern day compression, you usually don't rely on a single method, but you chain things together in an interesting way to squeeze the last little bit of redundancy out of data. And run length encoding is a fundamental part in the bzip pipeline that we will look at the end. So let's see what this is about. A simple form of repetition is the same character repeated many times. And an obvious application of this might be a black-white scan of a text page, say, where you have some text. You can hopefully see this. If you were to represent each pixel by a single bit, for just black-white, that's enough, not grayscale, black-white in the literal sense, you would expect to see many runs of zeros for all the background, and maybe even runs of ones, because the resolution of the scanner is much higher than individual widths of the characters, of the glyphs. So you expect to see many runs of repeated characters in such an application. And run length encoding is brilliant for picking these up. Indeed, we will restrict our attention for this unit here, for this subsection, to just a binary source alphabet. Already for Huffman coding, we were restricting attention to a binary coded alphabet, but now we'll assume the same for the source alphabet. Just to make our life a little easier, you can generalize the ideas to larger alphabets, but indeed it's often used on binary inputs anyways, because, as I said, it's used not as the first step, but after other methods have already done their magic. So a simple example of run length encoding here, is if we have this input text. So I just want to illustrate the idea. The first step is we parse this input text into phrases, which are just runs of the same character, right? Okay, so here we have 5 times the 0, 3 times the 1. So we would always group these together. As long as the same character repeated, it's the same phrase. That's something that that we will use in this section. A phrase is a part of the source text that we encode as one step. So we have to encode these phrases, and well, obviously for a binary alphabet, it's enough to store what was the first bit in the source, 0 or 1, and then what's the length of each subsequent run. We don't have to store which bit it is, because runs have to alternate between 0 and 1 if the alphabet is binary. So in our example, we would write a 0 for we start with 0, and then 5, 3, 4 is the length of these runs. There's 5 zeros, 3 ones, and 4 zeros again. These 4 numbers completely specify this source text, and that one has, well, what is it, 12 bits, and this might be, hopefully, be represented in fewer bits. So that part of run length encoding is very easy. The question that remains is, how do we encode these run length numbers, which can be arbitrary integers, in binary? For that, we have to think a little. And to get you started, I'd like to ask you to think more generally. How would you approach this problem of storing a string? Think of your favorite programming language. It probably supports strings. It would be a really weird language if it didn't. And probably these strings can be as long as you wish. You can specify a string of arbitrary length as long as it fits in memory and blah, blah, blah. But there's no built-in limit usually for the length of a string. How does such a language represent a arbitrarily long string? At the end of the day, it has to reside in main memory. It has to be stored in your computer. So you have to have some way of encoding it in binary. And that's the same question that we're asked here in run length encoding. We have arbitrarily long integers. At the end of the day, these are binary strings, so it's the same problem. How can we represent a string that can be arbitrarily long if the only thing we have is a large binary memory where we have to store things just using zeros and ones? Think about it for a second, and I'd like to see a few more answers. Maybe you can help me out and type something. Think about your favorite programming language. All programming languages have found a solution for this. So they all have solved this problem. Maybe you wondered sometime before how they do it. Let me show what people came up with so far. The first suggestion is a linked list. You could use a linked list indeed, provided that memory management is there for you. A linked list essentially solves the problem by reserving a pointer for each bit in the extreme case, or for each character. And you would have a special symbol that says this is the null pointer, right? That says there's no more next character. That's a way to do it. It would be inconvenient in this case because it takes a lot of space to store all the pointers. It is true that we can assume the length is a multiple of 4. If we store the length in bytes, or well, bit strings whose length is by definition a multiple of 4. Why would every bit string have a length multiple of 4? Anyways, you could make that assumption. My claim is it doesn't make the problem fundamentally easier if you have this restriction. Linked lists are great, guys, but they're very space inefficient because you would need a way to store pointers. and that pointer needs as many bits as you have space in your entire memory. So that really grows beyond any bound. Using graphs sounds like you use pointers, unless you get more specific. It probably has the same issue that pointers need a lot of space. I'm not sure how KMP helps. In chunks and join them. That's a good engineering trick. Instead of using linked lists for every character, you definitely want certain chunks of a certain length, and you could use pointers again. But remember, if you don't know any upper bound on the length of the thing you store, pointers are a problem. Variable-sized arrays, that sounds good, but how would you do that? A string of arbitrary length is, in a sense, an array of arbitrary length. How do you store an array? How do you store an array of arbitrary size? So maybe keep thinking about this a little more. It's sometimes fun to think about these very fundamental problems that obviously have many good solutions, because we use these solutions all the time. All right. I'll tell you a solution for the special case that we need. And we can revisit the other more general question. I can tell you what the solution is in Java, for example, if you're curious. What we need here is an encoding for integers. So we don't really need 0, so we can start at 1. But we need the encoding to be prefix-free so that we can represent all possible integers, and we can decode that unambiguously. That's the key thing. The challenge is to know when to stop reading. Well, that's same thing as saying prefix-free. If it has to be prefix-free, it must be obvious when you have to stop reading. So how could you do this? There's a very simple solution, which I'm sure, well, this is not what you would come up with, but it's actually very simple. You can obviously do this. You'd use the unary encoding, which means to specify a number, you write as many zeros as that number is, finished by a single one. That's a great encoding. It works. It's just super, super bad in terms of space, right? It takes as much space as the number is big. And you could actually represent 30 with just, 5 bits, and now you expanded it to 31 bits. And, well, we started with run length encoding to get rid of long runs. Now to store the runs, we produce long runs. Maybe this is not the solution yet. But we still build on this. And the trick is to see this as the base case of a recursive construction. Not sure if this is helping you. The standard binary encoding of numbers is actually fine. It's actually very efficient. The problem is that it's not prefix-free, right? If I write 101, you don't know if that means 5 or it's actually the prefix of an even longer number like 10. But the encoding itself is space efficient. So what we'll do is we'll store the length of the binary representation in this stupid unary encoding, which is space inefficient but prefix-free. And then append the binary encoding. Now that we know how long it is, it's no longer ambiguous. Okay? That's the key idea of Elias gamma code. Once you start thinking about this, you immediately find that there's some obvious ways to improve upon this. First of all, the length is always at least 1 bit, so we might not have to store exactly 7 bits here, but we can store just 6 zeros because we never need the 0. That's just not needed in our application. And also, the binary representation of any number, if you leave out all leading zeros, necessarily starts with a 1 by definition. Otherwise, you wouldn't have taken all the leading zeros away. So there's no need to store that 1. We can start 1 later. Okay? But that's just minor twists to the core idea, which is store the length of the binary encoding in unary and append the binary encoding. So what that leads to is for 1, the binary representation is a 1, just a 1. The length of that is 1, but we store L minus 1 zeros, which is 0 zeros. So 1 is just mapped to 1. The number 3 is 1, 1 in binary. That's what you see here. The length of that is 2, so we prepend 1, 0, 1 less than 2. One more example, 5 is 101. Length is 3, so we have to prepend 2 zeros. 30 happens to be this. Length is 5, you prepend 4 zeros. There you go. That's Elias gamma code. That's a way to represent an arbitrary integer. It can be as big as you want in a prefix-free way. And as you might see from this, we take the binary encoding and we make it roughly twice as long by adding this bunch of zeros. So the code word length for a number k is log k to represent that number, and then twice, plus minus 1, minus 1 I guess, because of the 1 0 less, and maybe minus 2 actually. But this is roughly what you get, whereas here it was linear. Okay, so that's the important difference. Before we come back to the string question, let's practice this one. Here is a bit string. There are more numbers encoded here, so you're just asked to decode the first integer in Elias gamma code at the beginning of this bit string. I'll show you the code again. You have the bit string in the question. I added more bits to the bit string so that you don't have the obvious separator, so you really have to figure out the encoding. So your answer should be a decimal integer, right? I'm asking you to decode, so this should be again a number in capital N in the natural numbers. So don't send me the bit string. You want to decode that further. Okay, you might need a second to do this. And we'll go through an example after that together. Okay, lots of suggestions. Let me show you some of them. Okay, maybe let's just go through this together. Or I'll leave the question open and just go through the examples, and then you'll try again if you haven't done it yet. So let's see some examples, and you can work out on the other one on your own. First, an example for encoding, and this is the full run length encoding now, which uses the gamma code for storing the run lengths. Okay. So, but you'll see this involves lots of practice examples of gamma code. So it works fine. We have this long bit string. We start by first noting what is the first bit, 1 or 0. Well, it's a 1, so we store this. Next, we store the run length, and this is 7 bits. So how do we store 7? Well, 7 is 111 in binary. The length of that is 3, so I have to add 2 zeros in front. And that is what has happened here. That's the 7. The next run has length 2. The 2 is 1 0 in binary, prepend a 0. That's what you see here. Another one, we have just the 1. So we remember that was just mapped to 1. Maybe we don't have to do that one again. Okay, good that I already counted this. 20 zeros. Now, 16 and 4 makes 20, so that's 20 in binary. And adding 4 zeros in front gives you the code for 20. And another one, 11 ones at the end. 11 is 8 plus 2 plus 1, so it's a 1 0 1 1 in binary, and adding the 3 zeros to code the length gives you the result. So that is the coded text for run length encoding of this bit string. That's the entire method now in its full glory. Let's see how well this worked. If you count here, that was 26 bits in the coded text and 41 in the source text. But that's down to 63%, which looks great. But also, of course, this was a fairly favorable example for run length encoding. Now let's practice some decoding. And again, this is a run length encoded bit string. So it will follow the same pattern. The first bit is telling you what is the first bit in the source text. So it's a 0. And now we have to start reading the next number. So what you do is you look for how many zeros you find. In this case, there's 3 zeros, so the length of the binary representation of the run length is 4 bits. So you take the next 4 bits and decode that in binary. Okay. That happens to be 13, 8 plus 4 plus 1. So you know you have the 13 is the encoded number. And so you write 13 zeros in the decoded source text. Okay. And then you continue with the same procedure. You count how many zeros do you find. That's 2 plus 1. So you have to read the next 3 bits and decode that as a binary number. That is 4. So you append 4 ones. Okay. One more time. You start, how many zeros do you find? Well, no 0. So you just read 1 bit. That's a 1. So it's 1. The next run length is just a 1. So you append 1 of the next flip bit, which is 0. And one more time. You count the number of ones. There's 1 at the number of zeros. There's 1 0. So you read the next 2 bits. That's a 2. So you append 2 more ones, and that's it. Okay. Do people want to go back to the example from the question? So let's do this one more time here together. This is not run length encoding, so there's no leading 0 or 1. It's just numbers. So we count how many zeros we find. That's 3. So we have to read the next 4 bits as binary number. That's these 4. That's a 1 plus a 4 plus 8. That works out to 13. So 13 is the correct answer. I see people need more practice for this. I know this is really, really, maybe you want to see these, but I'll lock it. I know this is really, really detailed stuff. You will have more opportunities to practice. Good. Let me see if I can jump over some of the many slides for this example. Good. So that is run length encoding. It's Okay, I thought I had some pseudocode, but maybe it's not needed for this one. You can extend run length encoding to larger alphabets, but then you have to say what is the next character that is repeated. For binary, you didn't need that because there was only one other character. It's actually used in some older formats for images, especially for scans. But again, as I said, in isolation, this is not the method of choice. You usually use it as part of a larger pipeline of compression methods. It is simple. It's also fairly fast. In the best case, it achieves remarkable compression from n bits down to log n bits, roughly, factor 2 or so. But this only happens if you have very few runs, very long runs of the same character. But this is the potential gain from run length encoding is much, much bigger than what we've seen before with the character encodings. There's no way you get sublinear with any of the character encodings, whereas with run length encoding, you could potentially get exponentially smaller. However, for typical types of data, if used in isolation, it doesn't really give good compression. You need, if you work out exactly how many bits you need to encode the numbers with Elias code, you will see that if the run lengths are not bigger than 6, then you don't get any compression. And you actually get worse. You get expansion whenever you have runs of length 2 or 6. These happen to be the two numbers that are represented with more bits than necessary. Or more bits than the unary encoding in the original source text would have taken. That's all for run length encoding. If you have questions, as always, just put them in the Q&A. We have 10 minutes left for today, 9 minutes left for today. That will not be enough to discuss all of Lempel-Ziff-Welch, but I want to get started so that we don't waste full 10 minutes. So this will be the first part of this only. In the next subsection, I want to discuss the first method that is used as given in practical application, and that's the Lempel-Ziff-Welch compression algorithm. I want to first motivate this with a little warm-up exercise. It's a little wordplay, not necessarily to be taken too serious. It definitely is about peas porridge. I had to look this up when I moved here. This is some British local cuisine, not scouse though, but it exists, and it's some type of stew or soup. Doesn't matter too much. So the core idea of Lempel-Ziff-Welch is to represent parts of the text using parts of the text that you've already encoded. And this is very nicely illustrated in this example. And I want to also shoot up the question for this. I'd like you to give me the content of this second to last row, so this one. I won't really explain how this works. I think it's the graphical explanation is self-explanatory. And it shows that for some texts, like this poem, which is fairly repetitive, as you will see if you decode it, you only really store the printed letters, and the other boxes are just a number or a pointer back to the coded text. So these take a certain fixed small amount of space. So it might already be obvious that this is a method that can, again, drastically reduce space. And it works fairly well for a variety of data, in particular, also for natural language text. Yeah, I see one good answer already. Maybe I'll just leave it open for a sec, but then you don't see this picture anymore. I probably have to just be a little patient here. Okay. Maybe at least 2 more people can send in their answer. The ones I got so far are fine. Mostly. So maybe I should add a word of explanation how this should work. If there's a box that's empty, then there is an arrow attached to it, and you should follow that, and that will point to somewhere where you can copy what goes in this box. So this 4th line says 9 days old because you copy this substring from cold. Now sometimes you copy something that's actually not there itself, but is copied from somewhere else. So here you have this this peas porridge. Well, that itself again is not fully here because you have certain things that are copied from other places, like here again. So you have to follow all these pointers. But if you do it, then it'll read like peas porridge hot, peas porridge cold, peas porridge in the pot, 9 days old. Some like it hot, some like it cold, some like it in the pot, 9 days old. I'm not recommending eating 9 days old peas porridge, but that's what it says. So yeah, many of you got this. Good. Let's see how this connects to a more serious discussion of Lempel-Ziff. But the idea is exactly that. Use references to previously occurring things. But let's start from scratch and properly. Huffman coding and run length encoding both talk about single characters, either by their frequency overall in the text or by being the very same thing repeated, but we don't have that so often in many inputs instances. What we more often find is that substrings, certain phrases or words, are more frequent than others. For English texts, these are the most frequent ones, and I'm sure you would have found others in other languages. Stuff like in HTML, you often see these things as combinations, and there's many others. And I guess you can imagine how this goes. Now you could think you could try to put some application-specific encoding together where you give a special character for these phrases that you think occur often, or maybe you could try to find out which phrases are more frequent than others. Yeah, let's stop the poem now. You can check the recording and go through this again if you want in detail. So you don't want to hard code this, or you don't want to have to specify or divide phrases into this is frequent, this is not frequent. We want a method that organically finds these by itself. And Lempel-Ziff does exactly that. It's a family of compression algorithms, not a simple thing. The idea is what you've seen in this poem. You have a certain part of the source text, and instead of encoding it literally by giving all the characters, you say, I've seen this before. It occurred at position 5 and the following characters. So you store things by a reference, and I will be very precise and concrete when we discuss the actual Lempel-Ziff-Welch. So a code word here is no longer encoding a fixed thing in every instance, but it encodes a single character or a substring of something we've seen before. And depending on the source text, that can be a different string each time. The important part will be that both the encoder and the decoder must have seen that substring before. Otherwise, you could not decode it again. But this will work out. There are many variants of Lempel-Ziff. They differ in the details of what is allowed. The original version would allow copying something from itself. Not sure if that makes a lot of sense. It's also, can you only copy things that were a phrase before, or can you start at any point? That's the differences, but we won't discuss that here. We'll focus on one representative variant of Lempel-Ziff, which also is the cleanest and the most widely used in practice. And that is the Lempel-Ziff-Welch algorithm. So historically, Lempel and Ziff came up with the core idea in a sequence of papers, and then Welch later rephrased it a little bit and added more twists to that, just make the method a little rounder for implementation. But the historic context aside, we'll just look at the final results from this history. I won't go into the details, but I just want to today I just want to give the core setup. Lempel-Ziff-Welch will be an instance of a variable to fixed coding. So we will fix a length for the code word. A typical choice in practice is 12 bits. And then all the code words will use exactly k bits, but they will represent a variable portion of the source text. And this is the opposite of what we used in Huffman. There we had a fixed to variable encoding. Fixed was one character is encoded at a time. Variable was the length of the code word. Here we flip this around. We do it just the opposite way. We represent something of various length, and the method will have to tell you how this works. And it's represented by a fixed length code. More details about this next week. Then we will finish up with Lempel-Ziff and also dive through the rest of the compression unit. Don't forget the tutorials later today at 4 p.m. You will discuss the tutorial for Unit 6, so it will be all about suffix trees and suffix arrays again. And then next week we'll have a tutorial about the compression methods, and by the time we should be through with all the content for that as well. Yeah, as always, I'm here for a chat in a couple of minutes if you have anything to discuss. So yeah, I think that's all announcements. Remember the deadlines. Check the Canvas homepage for the module. There you'll see the things listed at the bottom. So see you next week. Have a nice weekend. We'll see each other again next Tuesday, 11 a.m. Have a nice week. Bye till then. Or in a few minutes on Zoom, if you want. Bye for now.